attributes, we focused on the first 22, which excluded the target variable rain tomorrow. These include both numerical values, temperature, humidity, and one hot encoded categorical variables, such as wind direction or rainfall categories. So one of the advantages here is that the data set was already encoded. We didn't need to spend time transforming categorical features. It allowed us just to plug the data straight into our models and focus on feature selection. Overall, the data set provided a diverse and structured foundation for evaluating how different subsets of features affect predicted performance. In this slide, I've summarized the three feature selection methods we evaluated in our experiment. Each method uses a different approach to assess whether the features are useful for predicting rain tomorrow. The first is select K-best, a type of ANOVA F-test, to score each feature independently. It's fast, unreliable, a univariate method, and it identifies variables most statistically associated with the target. Then we have recursive feature elimination, RFE, with logistic regression as the estimator. RFE starts with all features and recursively prunes the least important ones based on the coefficients. A wrapper method that looks at interactions between features. And then finally, we employed random forest feature importance, which is an ensemble method that assigns importance scores based on how much each feature reduces impurity. It's particularly robust for multicollinearity and works well with data types that are mixed up. So by comparing these methods, we tried to uncover not only the best features, but how consistent these methods are with one another. So to evaluate the impact of feature selection, we designed a consistent testing framework. So all selected feature subsets, regardless of the selection method, were evaluated using a stacking classifier, which had already outperformed other models in our earlier baseline tests. So we tested 4 different subset sizes, 5, 10, 15, and 20, which allowed us to observe whether more features always led to better performance or if there was like an optimal sweet spot. We used an 80-20 train validation split, ensuring that the class distribution was balanced in both sets, because the primary performance metric was the F1 score, because we did detect some degree of a class imbalance, so we thought that the F1 score would be the best performance metric to evaluate, because accuracy can be quite misleading. So we monitored accuracy and calculated ROC to support our analysis. This setup allowed us to compare the outputs of each feature fairly. We visualized in this line plot how the model performance evolved as we increased from 5 to 20 features. So you can see both F1 score and accuracy plotted for each method. Select K-best, RFE, and random forest. So we see a clear pattern that performance consistently improves from 5 to 15. But after 15, the F1 score and accuracy start to plateau, and in some cases they dip or stagnate, which means diminishing returns. Now, this trend points that there are feature redundancies. Anything beyond 15, it just adds noise, and really there's not much signal there, which implies something very important, that adding more data doesn't always help. There's a point where simplification is better and stronger, and might even won't even compromise our performance. The next slide is a heat map. The heat map highlights the pairwise piercing correlations between features. So many features show low to moderate correlation. A few do stand out. For example, there's a strong correlation between humidity at 3 p.m. and then 9 a.m. And then there's also strong correlation between temperature at 3 p.m. and max temp. So both of these are above 0.85. This suggests that there is some degree of multicollinearity, which isn't necessarily harmful for all the models, but if you're using logistic regression or linear SVMs, it can violate the assumption. So while the stacking classifier is used to this sort of relationships, we can combine or drop these very redundant variables in future iterations. So the heat map not only validates some intuitive patterns in the weather of the data, it also highlights potential directions for deeper optimization. In summary, we found that feature selection improves our performance. Select K-best gave the best results with simpler logic and interpretability. And later on, for future iterations, we wanted to try maybe PCA instead of just wrapper methods, and maybe see the impact of the multi-collinearity that we found shown in the heat map. Thank you very much.